do a couple different things now. So the next thing on our agenda is to show you how to do some of the calculation of the centrality scores and some of the other cohesion metrics. The old-fashioned way, if you will, the non-IGNet way, just using the direct code. So that you can see how that works. Because we just did it in the fast way, we perhaps completely unfairly given Madelynn only a half hour to show you this. So, so this is one of those things that's left to the exercises largely, but Madelynn has agreed to be a good sport and show it to you anyway. So Madelynn Wellons is a graduate student here in sociology. She just defended her proposal and is now EPD. Working on social networks and mental health, particularly, and our mental health and aging, and some work on sleep as well. So a whole array of things that have to do with networks and health. And take it away.
Awesome. Great. Well, thanks all. I'm definitely not going to cover everything that's in this file. I'm going to skip around some of like the plots and stuff, but it like helps you visualize. So feel free to, it's on the Google Drive, so feel free to go through this on your own time as well in case I skip something that you think is really cool. So first, we're just going to clear the old data, load these packages and all that. And now we're going to import this data, which I think I actually already did. Yep, here we go. So the data is all in. It's the AHS network. I believe this is the same one that we were using with Leanne. Is that right? Okay, cool. Okay, so first we're just going to go over some of the first like fundamental things. So network size is just this command. So you just run that and it'll give you, so there's 440 nodes here. Then the number of edges is just, a lot of these are pretty simple, just telling you, it's like network dot and then whatever statistic it is. So there's 2,099 edges, and then the number of dyads, which is node pairs, is a lot, 193,000 and some change. And now we're going to get into the big meat and potatoes, which is a lot of the centrality measures. So first, total degree centrality, which is, again, just degree and then the network, and that is loading. Oh, right, because you have to just load degree, right? I was like, where's the output? And then here, so we're going to run it both in degree and out degree centrality, and then I'm going to show you one plot because it doesn't come out as an output. So here's, oh, the margins aren't working. But essentially, I ran out. Yeah, I don't know why the margins are too large. That's weird. Let me see if this works instead, because this is the nicer plot anyway. Nope, all the figure margins are good. This was fine on my end, so I don't know why it's being weird now. I'm gonna just try and clear everything first, and then do it.
I think if you pull up the plot thing, it might work usually.
Really?
Because, yeah, I think it's saying that.
Oh, it's like there's not enough space for it to go.
Mm-hmm. So sorry, I have it on my bottom, which is.
Like this?
Yeah.
Okay, let's
So
try
just
that again
give it a
then.
shot.
Oh, because I just destroyed everything. That makes more sense. Okay, let me just try and reload all this again. Sorry. Total degree, in degree, out degree, and then plot. No, it's still not giving me anything. Figure margin's too large. Well, we can just skip I was going to skip the plots anyway, so we can just skip the plots. This worked fine on my computer, so I don't know what's happening. Oh, okay. That's probably just a weird setting on here. This is why I should have used my computer instead of games, sorry. Okay, so okay, so we're going to skip the plot part. So this is plotting a lot of these in degree things once again, and here you can like put which Gabe's gonna go over later, is you can set vertex attributes and like node attributes and stuff. So there's a way to like essentially make one of those nice plots and have the centrality be shown as like maybe the size of a circle or something like that. But Gabe will go over that. This is just more of the degree. So here's closeness centrality. Let's see if a histogram works. But essentially, no, it's not going to do that. But this is the closeness centrality just for each node. It'll show you the close. Yeah, that can't be closeness because that's all zeros.
Maybe it's rounding.
Maybe it's that's probably it, because it wasn't. Yeah. let's see, on just the largest, strongest component, I might need to just swap out our computers, honestly, because I think you might have settings on here that might be having, because it was coming in fine for me earlier. I'm not 100% sure why. But let's try closeness 2. So this is, yes, okay, so closeness 2, so this is just focusing on the largest strong component like Jim talked about for components earlier. So this is just another variation of closeness. And now we get to the good stuff. So the more often used version, so Bonasich, I always pronounce that wrong. Bonasich centrality we can calculate on just the largest strong component only. And here you're getting a matrix. A lot of these outputs are going to be matrices, but again, you can plot these all and it'll show up really nicely. We're just not going to do plots because there's not enough time. And then we're doing it again with a lower beta parameter, which I think gave relatively similar results. Yeah, relatively similar results. And then we're just going to go through this again, just more. Sorry, a lot of this is repetition. Okay, and then this is running them side by side. Okay, and now information centrality. Did you go over information centrality? Okay, information centrality is, like it says here, it's a hybrid of closeness and Bonasich. So high information centrality indicates a large number of short paths to many others. So it's a lot talking about like diffusion of information. So to do that, you're just going to do pretty simply info cent and then the name of the data set and then rescale. And you'll see these are all very small, which makes a lot of sense given that it's just so many nodes. And then betweenness centrality, again, a lot of these are really similar, so sorry if this is just very dull of like, here's one thing that you can do, and then it's the same thing. But it's just pretty similar commands, which is also convenient though for doing these. So, and then one thing that, this tutorial was made by Molly, who is left in 2020, I think she graduated. So she did something really cool here, which is she was like looking at how to like rescale things. Something you're gonna have to do in different aspects is you might have to like log something or square root something to make things be actually comparable. And here that's one thing that Molly noticed, like some of these were like in the thousands and a lot of these were like 45 and things. So then she did square roots. This is not, okay. Gabe, can we do a quick switch out? Because that's like not even showing me half of the stuff anymore. So I think that's probably just would be better to just. Yeah. Yeah, just like won't go beyond 388 for some reason. I don't know what's happening. No, you're good. It's not your fault. I'm the one who took your computer without a test run, so it's definitely my fault. Okay. Is it running okay on everyone else's? Yeah. Okay, cool. That is good to know. Yeah, our studio will load. Okay. Okay. Let's try this again. Okay, perfect. So we were at the comparing closeness. Sorry, my computer is old, so it's gonna take a minute. Okay, here we go. Okay. So we were at plotting between. I'm gonna show this plot as well, just so we can see. So this is, for example, one of the plots you would see if you're in it. So this is sort of plotting the betweenness centrality. And then one thing that we can do here is also that we're going to do a bit later in this as well is comparing different types of centrality measures, because as we talked about, they're very different. So this is a plot that's just comparing in degree and betweenness in the largest strong component. You can do that with all of your data if you want to. It's just in this tutorial we tend to focus just on the largest strong component for a lot of these centrality measures, at least, not for later. Okay, so now when we're comparing centrality measures, this is in degree and betweenness on a different scale, so you can sort of see it's a bit weird in that it's like everything is a circle, but you can sort of see comparison-wise like that it's relatively linear, but not entirely. So there's definitely differences. You can compare correlations of these as well, which I would highly recommend. That's something that I do when I'm running a lot of analyses and I want to make sure that I'm using measures of centrality that are either working together, or I need to know if there's something that's going on that's like, if they're going to be relatively different, so you can see how well they're correlating and if that might tell you something about your data or about how your measures of centrality are working together. Now we're going to move on to centralization and whole network measures. So there's density, which is pretty straightforward. Again, like a lot of these, it's just GDEN and then the network. And then we have degree distribution as well. We have 3 different histograms you can see. So you can see like the in degree versus out degree versus total degree. So these are just some nice visualizations for some of these densities, and degree distribution is like one way that I think of it as well. Sort of just like comparing everything across like different measures. So you can help figure out, one, what measure you want to use, and then also what measure might be best for you to use, what measure might seem the most normal, or just sort of testing your hypotheses in a sense of like what you think is going to be a good measure to use, like making sure that it's actually going to work. We have a bit of clustering. Did you go over clustering coefficients or no? Okay, well, I'll show you how to calculate it, but this is just a measure of transitivity essentially. And then this one, because we skipped triads, that makes sense. Okay, so there's a bit of, this is some of the things that Jim would enjoy. We're about to move on to triads and dyads. But transitivity is related to triads. These dyads, so this is symmetric dyads, seeing like who is, like if it's, they're directed towards each other, so not just one person sending a tie and the other one's like not sending a tie to that other person. There's an edgewise ratio, which is, again, pretty similar. It's just G recip and then the network. And then here is Jim's favorite thing, the triad census. So it'll tell you all these different types. It's here at the bottom, so it's kind of hard to read. All these different lists of triads here, and just like the number of them that's in each. And then we have more component stuff as well. So like we talked about, we did this a bit before when we talked about wanting to use strong components in this. So we're just gonna, this is just like an easier way to figure out how many components there are that you think are fitting these categories. So here's strong, there's 73 strong components. Weak components there's only 4, which is, helpful. Examining the strong component, or the people that are in them, sorry. Not the number of components, the number of people who are in that component. So the strong component, if you want to look at it, you can see, I believe this is as a list. So it shows you the component as a list. So here we're going into the list and going to membership. So if you run that, that shows you essentially the member, like each person, which sort of like components they're a part of. And then here is when you can see the size of each component. We're going to run a little histogram. So you can see a lot of them are very small. Most of them are extremely small. This is very right skewed because there's a couple of components that have like 100+ people in them. But most of these are, in like the 4 to 10 range. There might be some like 20s.
Most of them are isolates and I say diads.
Yeah, that's true. Yes, most of them are much smaller than that. So here are some by components, which in ad health, it makes a lot more sense because it's in these large connected networks. By components might be more helpful. So seeing the size of these by components, we're going to do another little histogram, and you'll see that's a little bit better in that it's not just like one at the end. It's a little bit more informative. But yeah, so a lot of these, again, are just, it's going to create an object, and you're going to go into the list object. I think Tom talked a bit about lists. You're just going to do the little, like the $sign component, and that will then let you go into part of the list and pick out, like, you're essentially going into this object list, and you're picking out this thing from the list. That way you don't have to go in the manual way, which can be kind of annoying sometimes, especially if you don't know exactly what you're looking for. And now we're going to do some cut points. How am I on time? Oh, okay. We have plenty of time. So calculating cut points. Here you go. So again, a lot of these commands are pretty simple. Running the cut point node. So here's another little very pretty graph that Molly made up. So this is just graphing all of these cut point nodes. And then I think I was planning on skipping K-cores. Did you want me to go over K-cores, Jim? Okay. Yeah, and then clicks are also, I think I was going to skip. But so that is the really, really, really fast version. I purposefully left time here because I have a feeling there will be questions. Because a lot of this was very, it can be straightforward, but you have to be familiar with the commands. So to me, I'm going through this and I'm like, oh, this is straightforward because it's just this command does this and this command does this, but that's not how it is for a lot of people. So yeah, if you have any questions. Yes.
I have a question about visualizing degree distribution. So when you get the in degree, out degree, and total degree distributions, are there particular patterns we should look out for, or anything is okay?
I think it varies based on your data.
It's going to depend if you can scroll back up to your,
Yeah.
or just back up to your, you don't have to rerun it, you can just tab back to the distributions there in your visualization window. Just the arrow back, I think.
Oh, right.
Yeah, just go back. Go back to that where you had right there.
Yeah.
So that's a pretty classic in-degree distribution where most people are not particularly popular, but a few people are really popular. So you see that one person has about a degree of 18. The out-degree distribution is both, it's probably the most important thing in a directed network like this, but also in some ways the saddest, because you'll notice that it maxes out at 10. That is not reality. That's the survey. So the survey wouldn't let you nominate more than 10 people. So everybody has a max degree of 10, or everybody who has a max degree has a max degree of 10. They don't have any more. And so the reason that the out degree is so much higher than the in degree is purely a function of the survey design. So yes, it's very important to go and look at these distributions. And the thing you should look for is there a cap? I mean, you should know that from your survey, but if it's data you didn't collect, you might not know that. So that's a good thing to know. The total degree, if I remember right in this case, that the way iGraph is calculating total degree, it's actually the in degree plus the out degree. It's not the joint degree, which is a slightly different critter. But again, because this one is swamped by the in degree, you're going to get a distribution that looks almost like the in degree distribution. What's interesting here is there must be a count, not a percent, because it can't possibly be that 60% of the people have zero out degree. But you can see here that all those zeros that are in the out degree distribution and the total degree distribution now are taking you down to the arrows drawing down the bottom, the low end of that histogram. So that's the kind of thing you would look for. I think one of the key elements when you're thinking about these local metrics is remember all of them or all of these node level metrics are designed to figure out. Let's see this well. All good metrics are unidimensional, right? A measure means one thing and just one thing. And so each of these metrics means one thing very well, but networks are composed of lots of different things. And so the reason we're throwing at you a bucket of different indices is that often you want to think about what one thing matters the most for the process you care about. So the centrality scores are each trying to get at one of these dimensions. So it's the proportion of the times that other people in the network nominate me, that's in degree. The number of times I've nominated other people, that's out degree. the extent to which I have a capacity to break someone's network, that's whether I'm a cut point or not, right? So each of these elements means something very specific. And what's nice is that iGraph will calculate 100 of these things. And we could go through and describe them all, but that gets a little list-like.
Yeah.
And so what's useful to do is not to plug it, but go to the book and have a chance. And then we talk through the what and the why of each of these metrics, or at least most of them. And so the main thing that you'll end up doing, we're going to talk about this in detail on Thursday, is that the metrics are usually used to either describe qualitatively, when you want to say what's the distribution of kinds of people in my network, if the people that are have high out degree also have high in degree or what have you. But more commonly, it's used in a regression. So I'd say, what's the probability of someone smoking or not? And if I have a smoking intervention, or if I want to understand smoking effects, is it the isolates in the school? Is it the people in a particular cluster? Is it the people who are central in one degree or another? These kinds of features then are used to predict the likelihood of a person smoking or not. And so these, for those of you that are in the machine learning world, these are all features that you would then put into the model for feature selection, predicting something like smoking, for example. A couple of things I did notice here. You got to be a little bit careful. I didn't catch this before, but Bonacic centrality, if you're getting negative values, as you're seeing here, it means the beta weight is too high. You probably shouldn't run Bonacic centrality on disconnected components, which I think is we're also doing
That
here.
makes sense, yeah.
And so, because it's essentially it's a type of eigenvector centrality, so it only works if the matrix is invertible. If the matrix of multiple components is rarely invertible, and so those numbers are probably a bit nonsensical.
Yeah.
And so what you want to do is just identify so as far as an example goes, you want to just identify the largest component and run it on a smaller beta coefficient. One of the nice things about IdeaNet is that we do that for you. So we pick a sensible value, we pick it so that it doesn't go out of range, and we apply it to the right set.
Yeah, that's weird because this is on the largest strong component only.
Yes, but an exponent of 1 is impossible to manage.
Yeah.
Right?
So something's up.
Yeah, so it should be like 0.01 almost, probably.
I see.
Other questions or
Other
thoughts? Again, this was the world's fastest
Yeah.
wizard. What we wanted to do, we didn't. This was supposed to be mainly to get a sense of this kind of syntax. So if you want to know how to do these things, then iGraph literally, if you go to the iGraph manuals, has hundreds of these kinds of measures.
Yeah.
And so you have centrality underscore a bunch of different things, and then options for most of them. So it doesn't make a lot of sense for us to give you all of them. The thinking was to give a sense of how you calculate a few of them, and then you can go and get a sense of where to find them.
Is this MATLAB or
So this is StatNet.
This is StatNet.
Yeah.
You do this
This
with
is
StatNet? Okay.
Yeah, that's what Molly did. You can calculate a lot of these things in iGraph I think you can calculate all of these things in iGraph.
Yeah,
StatNet
I
think
usually
is
do this in iGraph. Interesting.
Yeah, I personally, it varies for me depending on, because I think a lot of the code is just a little bit simpler in StatNet, and I mean Molly had it all in StatNet, so I was like, I'm not going to change this all to iGraph. but I tend to do, I would say most of these things I do in StatNet, except when I'm doing just straight up eigenvector centrality, I do that in iGraph, just because, I don't even remember why, I think just because I was taught to do it that way.
The nice thing about StatNet is Carter, the underlying metrics engine for StatNet is SNA. Carter Butts wrote it. He's a sociologist, so it kind of fits some of our assumptions about the way these things work. Whereas iGraph is written by graph theorists, and so it tends to have a slightly different conventions. So it probably is a little simpler. Please.
Could you just talk briefly about the total degree distribution, versus the how many partners you have without counting reciprocals?
Yeah, here's
to
the total number of adjacent nodes. So total sent plus received. So yeah, it's just adding them essentially. Sent plus received for each person.
Right, but when you interpret the data, what does this mean compared to
Honestly, I don't really use total degree. is one way to do it. But I mean, because of the issue that when it comes to, at least when it's a large network, I don't use total degree, because then you come to this issue of, you're just essentially adding the in degree and out degree. But if you're using a smaller network, then it might be more beneficial. Like I'm using some text and call data of like 20 some people, and for that I find it a little bit easier. But even then, I still would use in degree and out degree, because a lot of that is sort of total degree is like a different version of your network size in a sense. So that's like one thing that you could do for
Yeah,
it.
I think it's the most interpretable thing to do is to use the degree on the undergrad.
Yes.
So when you
Yes.
have a network like this, where the out degree is truncated, then you can at least then assume the debate whether or not how to treat that. But it's usually more interpretable to think about the degree that is based on the symmetricized version of it. Right.
Okay.
And the problem, of course, is we usually think about a max symmetric. So anybody who's nominated me, we assume that I would have also nominated them. That's what we think a max symmetric. Because reciprocity is going to be constrained by the out degree. So because you can't reciprocate more than 10 ties, your own reciprocation rate is going to. So one of the nice things you can do there then is think about as a function, each person's, if you want to think about reciprocity, it's more useful, I think, to think about it as a function of a person's own out degree. So of the 10 ties that I've nominated, what proportion of those people reciprocate my nomination? Now that'll give you a better sense of the overall reciprocity rate than will a global measure, because the global measure has been constrained so much by this truncation. As a general data collection thing, I think Jimmy will probably go over this at some point, is that we tend to ask people to nominate a fixed number of nominations because it's a pain in the ass to sit and answer a survey for an hour and then list all 50 of my friends. And so if you want to get your respondents to respond to your survey, you simplify it and make it short and do it this way. It has huge downstream consequences to the analysis side. It fundamentally changes this out degree distribution, which is then the thing that determines like all the rows of the adjacency matrix. And it determines that, it determines the structure of the network as a whole. So when you make a decision about how you're going to limit the number of ties that people can respond to, know in advance that doing that is going to distort the vision of the network. To the extent to which that distortion is good or bad, like how much damage it does is going to depend on the context. And we'll talk about that in the missing data thing on Thursday. But it's this trade-off between the amount of time you can hope to get from your survey subjects and the amount of information you hope to do on your set. And that's going to be a balance that you have to play with in a given set.
Especially if you're doing longitudinal, because if you let there be no limit, then generally there will be a huge drop off from like wave 1 to wave 2. People will be like, oh, I remember filling this out for so many people, so I'm only
Once
going
they
to do
learn
it
that
for
you're
2.
going to be stuck in your chair for an hour and a half, they won't do it the next time. Right?
Exactly.
So again, there's this trade-off between respecting your survey, the time of your survey respondents, and getting the answer you want. And so a lot of the times you'll be better off, instead of saying, give me to your 10 closest friends, give me like the 10 people that you like are really that relationship that's really central to what you're trying to figure out. So if friendship isn't what you care about, but you care about discussing, who you smoke with, then there's probably a smaller number than that, and you're going to do less distortion when you have these kind of things. So think carefully about those kinds of designs. Jimmy, agree. Let's see what
You have advice on analyzing directed versus undirected networks. I tend to lean undirected because I feel like it's like faster or easier, but then you don't get things like in degree, out degree. Preferences, advice.
My recommendation is that it depends on what you're trying to answer. So I think in degree is a great measure. In degree is a popularity measure. It's really robust to missing data. It tells you something about the status structure and the setting. And so as a metric that's useful, in degree can be quite nice. As far as then, if you want to calculate closeness centrality or clusters or something like that, symmetricize the network and run those on that side. So it's going to depend a little bit on the metric. But any kind of flow process, because of this constriction due to out degree, I think it's symmetric and run on that. But I don't want to throw away the unsymmetricized data, because that, especially for something like a friendship or bullying or other kind of affectual relationships, the asymmetry is where your status structure in the system is at. And so most of these networks will have a hierarchical ordering, a status structure built into them. Like there will be kids that want to be at the cool table but aren't at the cool table, and that will be revealed by the asymmetries in the network. And again, looking at one of the nice things about, one of the things where the truncation degree doesn't absolutely kill you, is that if you find directed ties that then create cycles that indicates equality at the meso level because of the cycles that are doing it. But if those cycles then are embedded in a hierarchical structure, that's revealed. And so there are ways of getting at the information that's there, sort of hidden under the ties. But but for a lot of the metric construction, I do symmetric networks. Awesome. Thank you, Madelynn.